I will present our work, Graph Convolutional Networks for Learning with Few Clean and Many Noisy Labels. This is a joint work by Ahmet Iscen, Giorgos Tolias, Yannis Avrithis, Ondrej and Cordelia Schmid. Few-shot classification is a challenging task. The goal is to learn classification models with only a few labeled instances per class. For example, the shown image would be the only instance in a one-shot setting for the class Admiral, and we would need to learn a classifier using this instance. In this work, we propose to complement few labeled images with the noisy images collected from the web. We use the class names to query a web collection of images that contain free-form tags and captions. In this example, we use the query Admiral to retrieve additional images. We retrieve a set of images for this query. Our goal is to use appropriate subset of additional images with respect to the clean labeled image. In this case, we would like to use the images that contain Admiral butterflies. To this end, we propose a graph-based approach to clean noisy instances from the collected data. More specifically, we propose to train a GCN for the purpose of predicting a relevance weight for each instance. We first create a graph based on the pre-trained embeddings of each image. Each image corresponds to a node and is connected to n reciprocal nearest neighbors in the embedding space. We are given a small set of clean images and a larger set of noisy images, the ones we collected from the web crawling. We train a GCN-based binary classifier that takes the K9 graph into account. The goal is to predict the relevance weights of each instance for a specific class. The input is the n times n adjacency matrix, which represents the graph, and also n d-dimensional embeddings. The model outputs a relevance weight for each node. We train this GCN with a binary cross-entropy loss as shown here. The left term is for the k-clean examples and it pushes their output to be 1. The right term is for the n-k noisy examples and it pushes their output to be 0. Lambda is a hyperparameter which we call the importance weight. And if lambda is high, the weights for the additional noisy images are more likely to be 0. As we reduce lambda, this constraint will be more relaxed and the images that are connected to the clean examples will still get high weights. Here is the overview of our method. We start from one or few labeled examples. We query with the class name and collect additional noisy data from the web. We then create a graph using the visual embeddings of each image and train a GCN which outputs a relevance weight for each image. We then use these weights when training a classifier. Here are some examples of the generated relevance scores. First example is the Black Widow class. Below each image, we show the predicted weight. The top row contains images with large weights depicting different viewpoints of the Black Widow spider, whereas the bottom row contains the images corresponding to Black Widow, the superhero, that receive relevance scores close to 0. This is a typical problem due to polysemy of the class name. The second example is the Pineapple class. It is evident that compared to the single clean example, the variability of the positive training data increases by the included noisy images with large weights. In our experiments, this translates to higher accuracy when learning a classifier. For our experiments, we extend the low-shot ImageNet benchmark and we sample k-clean examples for each class using a subset of ImageNet or Places 365 datasets. We use YFCC 100 million for our noisy data. This dataset contains about 100 million images. It doesn't have any labels, but has free-form user tags and captions which we can use to query the class names. The feature extractor is trained on classes that don't overlap with the clean data. We use ResNet 10 and ResNet 50 architectures. We use 3 different classifiers in our experiments. The first one is the prototypical classifier, which basically computes the average embedding. In our case, since we have relevance weights, we compute the weighted average according to relevance. The second classifier is the linear classifier, which is a fully connected layer trained with SGD and cross-entropy loss. We weigh the training loss of each instance based on their relevance weights. Finally, we have the CNN classifier, which is basically fine-tuning the entire network, including the feature extractor. Similarly to linear classifier, we weigh the training loss of each instance based on their relevance weights. Hyperparameter lambda controls the importance of noisy data in the loss term when training the GCN. We tune its value according to the performance on the validation set. There is an apparent trend. We need smaller lambda for the cases where we only have few examples, and higher lambda as the number of clean examples increases. We now compare our method against some baselines using the prototypical classifier. We first show the accuracy in low-shot ImageNet benchmark for k equals 1 and 5, which corresponds to 1-shot and 5-shot scenarios respectively. These are the numbers shown in the red boxes. We now show the accuracy when using the noisy data without any cleaning. Beta weighting with beta equals to 1 corresponds to no cleaning at all. This brings some improvement for k equals 1, but the performance actually degrades for k equals 5. Cleaning with MLP is a variant of our method without using any graphs. We use the same loss function and the same architecture to train an MLP and predict relevance weights. This approach already improves the accuracy performance for 1-shot and 5-shot problems. Finally, we show the accuracy with our method on the bottom row. We see that our method brings significant improvement, especially for k equals 1. Because we're able to automatically mine for additional data, we can also use more training data for more demanding and powerful classifiers, such as the linear classifier or fine-tuning the entire network. We see that our performance continues to increase with more powerful classifiers. To conclude, we supplement few-shot learning with additional noisy data collected from the web. We propose a GCN-based cleaning method to choose the appropriate subset of noisy instances. Our experiments show significant improvement in accuracy. More specifically, we are able to go from 45.3% accuracy to 74.1% accuracy in one-shot learning setup by automatically mining and cleaning data.